Hey guys, welcome to the 80-second C programming tutorial, and in this tutorial we're going to be rewriting our linear search algorithm so that it's generic. So the first thing that we really need to talk about is the prototype. Back in our integer linear search, we needed to pass through an array, the length of the array, and a key value to search for. So we need at least that much information for our generic linear search, but we will need more. So let's go back to our integer linear search code to see what more we'd need. The first thing that we do inside the loop of our integer linear search function is we do array at the index of I. Well, we know that in our generic linear search, this array right here won't be an integer pointer. It will actually be a generic pointer, so a void star. And what did we learn about void stars a few tutorials back? Well, we learned that void stars cannot be dereferenced. So that means that these square bracket operators will not work on void stars. So we're actually going to have to calculate the address manually. And in order to calculate the address manually, we're going to be needing the length of each element inside of the array in bytes. And don't worry, we'll talk a lot more about how we're going to actually calculate the address of the current element in the array later on. But for right now, just know that we're going to need the size of each element in bytes in order to do that. So we'll need all of this up here plus the size of each element in bytes, so the element size right there. After we access the element at the current index, we then compare that element with a key to see if it's the same. And to do the comparing, we use the equal operator. Well, we actually cannot do that in generics since we could be comparing two fractions or two integers. We don't know. We obviously cannot use the equal operator on fractions, so we're going to have the caller pass in their own function to do the comparing. We could do a memCompare, but that's not perfect because let's say that the caller passes in an array of fraction structs and their key is 1/2, but inside of their array they have a fraction that's 8/16. Well, you and I both know that 1/2 and 8/16 are equal, but memCompare doesn't. So that's why we're going to have the caller pass in their own compare function. So this is all that we're going to need in the prototype, 5 things. So our prototype is going to look something like this. It's pretty big. The first thing is just going to be the array, which is obviously going to have to be a void star since this is generics. And the second thing is the LM size, and I decided to make its type size t since that's just sort of the C convention. And then after that we have the len, which is just the length of the array. And then we have the key, and the key also has to be a void star since this is generics. We have no idea what type the key is. It could be an integer, it could be a character, it could be some sort of struct. We have no idea. And then lastly, we need our compare function, and our compare function has to look exactly like this. So it's going to return an integer. If it returns 0, that means that the two things being compared are equal. If it returns some non-zero number like -1 or a million, then we'll assume that they're not equal. And this function also has to take 2 void stars because again, this is generics. We have no idea what two things we're actually going to be comparing right here. So now that we understand the prototype, let's move on to the pseudocode for our function. And if you're not familiar with the term pseudocode, basically what it means is it just means fake code. So this code obviously won't compile or anything, but it's just to give you a rough idea of what our function is actually going to be doing. So obviously we just have all of our arguments right there, and I'm not going to rewrite all those, there's way too many. And right here we're just iterating through every single element inside of the array. We're then comparing the current element to the key. If it's 0, then we return the current index, indicating that we found the key. If we get through the entire array without finding the key, then we return -1. And right here, we calculate the address of the current element. And that's exactly what we're going to be talking about on the next slide. So this is what the array is going to look like. We have no idea what each one of these elements are, nor do we care, since the caller is going to be passing in the compare function. But let's talk about the information that we do have. We have the array, which is just a pointer that stores the address of the first element inside of the array, and we also have the element size, which is the size of each element in bytes. So to figure some more stuff out, let's just assume the value of some of these variables right here. So we're going to say that the array is 1000, meaning that our array starts at address 1000 in memory somehow, and we're going to say that each one of these elements are 2 bytes in size. They could be shorts or they could be structs that have 2 characters in them. We don't know and we don't care. And we're trying to find the address of the element at the index of 3. So we're trying to find the address of that element right there. But before we jump to trying to figure out the address of this element, let's talk about finding the address of the first element, the 0th element. Well, we already have a pointer that just stores the address of that, so that's really easy. The address of the first element inside of the array is just array. But how about the element after that? How about the element at the index of 1? Well, we know the address of the first element right here, so we know the address of this right here, and we know the distance between here and here. That's lm size. So if we just add lm size to array, that will give us the address of the element at the index of 1, or the second element inside of the array. So that'll give us the address of this right here. What about the element after that? If we just add lm size to it once again, that will give us the address of this element right here. And if we add lm size to it a third time, that will give us the address of the element at the index of 3. So just to recap, to get the address of the element at the index of 0, we didn't add anything to array at all. It's just the address stored in the array variable. To get the address of the element at the index of 1 inside of the array, we had to add lm size to array once. To get the address of the element at the index of 2 inside of the array, we had to add lm size to array twice. And lastly, in order to get the address of the element at the index of 3, we had to add lm size to array 3 times. So if you haven't figured it out by now, this is the algorithm for calculating the current element's address. And now let's just go ahead and plug this into our pseudocode. So this right here is pretty much what our generic search algorithm is going to look like. It's going to look exactly like this. So let's just go ahead and go into code blocks and test our function out. So really the only thing that I changed from a PowerPoint pseudocode is I added in some semicolons and I changed this to CMP instead of compare, and just some very minor things like that. So let's just go ahead and give this linear search algorithm a test, but there are a few things we have to go over first. So we're going to be searching for this key inside of this array right here. So we have this fraction array called fracs, and inside of this fraction array we have 5 fractions. The first fraction is 8/9, 3/4, then 5/8, 1/2, and so on. So before we can actually call linear search, we have to do one thing. We have to write our compare function for comparing 2 fractions. So what we're going to do is we're going to say that this returns an integer, it has to, and then we're just going to go ahead and call it frac compare. It doesn't really matter what you call it, but I think that this name reflects what it's comparing. And then this function has to take 2 parameters, which are going to be the things that it's going to compare. So we'll say fraction pointer f1 for fraction 1 and fraction pointer f2 for fraction 2. Now you're probably wondering how I can do this, since the function asks for a compare function where both of the parameters are void stars and not fraction stars. Well, void stars will be implicitly cast as any other pointer. So right here, when it calls the compare function and it passes through the current element and the key, which are both void stars, it will implicitly cast those both as fraction pointers. So there's no need for us to do some extra work and then cast them ourselves. So in order to make sure that this compare function sees 6/12 and 1/2 as the exact same thing, what we're going to do is just go ahead and convert each one of these fractions into decimals. So we're going to convert both the fractions into floats first. So we're going to say float f1 val for fraction 1 value, and then we'll just set it equal to what the fraction would be as a decimal. So we just divide the numerator by the denominator. So we're going to say f1 arrow numerator divided by f1 arrow denominator. And right now it's doing integer division, since both the numerator and the denominator are integers. So what do I mean by this? Well, right now we'll say that we're dealing with 1/2. So 1 divided by 2 is 0.5, right? Well, in integer division it's 0, because integer division just chops everything off after the decimal place. So when we do 1 divided by 2 as integers, we get 0. So what we need to do is cast one of these or both of these as floats. And I'll just go ahead and cast both of these as floats so that it doesn't chop off the end of the quotient. So we'll just say float like that. And then we just need to do the exact same thing for the second fraction. So we'll just copy it and change some names around. Okay, so now if fraction 1's value and fraction 2's value are both the same, then that means both the fractions are equal. So we can return 0, indicating that both the fractions are equal. So we'll say if f1 val equals f2 val, then just return 0. If they're different, then we have to return some non-zero number. Anything that's not 0 will do, but let's return something fun, like hex beef. And if you don't really understand what this is, it's just in hexadecimal, there's letters A through F, so we can spell things like beef. So now let's just go ahead and test this out. We'll store the return value of the linear search function call in a variable called index. And then we'll just go ahead and call our generic linear search. That's why I called it G linear search for generic. And the first parameter of our generic linear search function is the array that we're searching through. So frax is the array we're searching through. The second parameter is going to be the element size. So the size of each element in bytes. And we have an array of fractions, so the size of each element would just be the size of a fraction. So size of fraction. And then the next parameter is going to be the length. So the length of the array. There are 5 elements inside of our array, so I just put 5 right there. And then after the length, we just have the key, which is a void star, so we have to pass through the address of the key. So the address of the key. And then lastly, I just have to pass through our compare function. And our compare function that compares two fractions is just fract compare. So fract compare. Alright, and then after we call this function, let's just go ahead and print out onto the screen the index that it got. So mod I, since it returns an integer, and then we'll just go ahead and print out that integer that it returns. So when we run this, we should get 3 out onto the screen, since 1/2 is at the index of 3. 0, 1, 2, 3, and our key is 6/12, but 6/12 is equal to 1/2 according to our compare function. So when we run this, we should get 3. And we do. Alright, so that's it for this tutorial on writing the generic linear search function, so see you guys.